Hi. So now that we know about what logarithmic functions are, today I want to talk about how we will graph logarithmic functions. We're going to use the fact that we know that logarithmic functions are inverses of exponential functions. It's going to come into play later on, so keep that in mind. We're going to try to graph y equals log base 2 of x together first. And I'm just going to start this with an xy table since we haven't graphed one yet. So let me say what happens when x equals 1. Well, log base 2 of 1, 2 to what power equals 1? Well, 2 to the 0 power equals 1. So there's going to be a point on my graph at 1, 0. Now when x is 2, do the log base 2 of 2. 2 to the first power is 2. So when x is 2, y is 1. I've got another coordinate on my graph here at 2, 1. All right, x is 3. Log base 2 of 3. 2 to what power equals 3? I don't know. So forget I used x equals 3. Let's try 4. Log base 2 of 4. Yeah, 2 squared is 4. So log base 2 of 4 is 2. So when x is 4, y is 2. So right, got another point there. Don't really know what log base 2 of 3 is. I could choose more values for my x's here. Notice that I'd like to choose powers of 2 because I need to know 2 to what power equals those numbers. So I could jump ahead to say 8 or 16. And log base 2 of 8 is 3. Log base 2 of 16 is 4. So I don't know if I've got enough room to put all those on here. Let's see. There, when x is 8, I know y is 3, and then kind of continue on. If I get out here to 16, you won't be able to see that on the video, but there'll be another point up there at 4. So the y values are getting bigger. Notice they're not getting bigger as quickly as we go. At first here, we had just a rise over run of 1 over 1. Here it's up 1 over 2. Here it's up 1 over 4. So while this function is increasing, it's not increasing as quickly as time passes. So we've only tried positive numbers here, and that's been on purpose because you can't take the log of a negative number. That would be undefined because you can't raise 2 to some power and end up with something negative. You say, well, wait, well, what if y is negative? Can I get y to be a negative number? I could. If y is -1, well then 2 to the -1, remember your negative exponents, x would be a half. Or let's say -2, in case you can't see that. When x is 1/4, y would be -2. So I would have more points here, 1/2, -1, 1/4, -2. And what's going to happen is, as the y values get more negative, the x values are approaching 0, but it'll never quite get there. So we've got an asymptote again. So this graph will approach x equals 0. It will have a vertical asymptote. I should write that in here. We'll have a vertical asymptote at x equals 0. X equals 0 is my vertical asymptote. Cross the x-axis at 1. Right? The x-intercept is going to be 1 for any of these log functions unless we start doing transformations, because regardless of the base, whatever number this is to the 0 power would give you 1. Right? So connect the rest of these points here, and our function's increasing, but it's also kind of leveling off. The graph's going to look something like that. That's the basic shape of a log function. Resembles a square root graph a little bit, or half of a parabola on its side kind of graph. Different though because of the asymptote. This function, as x approaches 0, as x gets closer and closer to 0, y is approaching negative infinity. This graph will continue to head down. You can get as negative a y value as you want. In fact, let's talk domain and range here. You can only use positive numbers for our domain. You can't take the log base 2 of a negative number. You can't take a log base 2 of 0. 2 to what power equals 0? There's not a number that does that. So my domain is just going to be positive numbers, the open interval from 0 to infinity. Now range can be anything. I can get negative outputs, I can get positive outputs, I can get a 0 output. I've got that x-intercept of 1. So the range is going to be all real numbers. All right, so there's your domain and range. And then I mentioned there was an x-intercept, when x is 1, comma 0. Right? So that's the basic shape of what one of these log functions looks like. And I mentioned that we have log functions. We know they're inverses of exponential functions. This log function in particular is the inverse of y equals 2 to the x power. 2 being the base of both the log and of the exponential. Well, think about what 2 to the x power would look like on the graph. You don't have to do this every time. I'm just trying to connect these two functions in your head again. If I put 0 in for x, 2 to the 0 power is 1. When x equals 0, y equals 1. So the exponential would have a y-intercept of 1. Notice the x and the y's have switched. That's what inverse functions do. They switch your x's and y's. And every point on this log graph would appear as a point on your exponential graph with the values reversed. Instead of 2, comma 1, there'd be a 1, comma 2. Instead of 4, comma 2, there'd be a 2, comma 4, and so on. And your graph of 2 to the x power will look kind of like this, you'll recall, with your horizontal asymptote. And notice that these two graphs are reflections of one another. They're reflections through the line y equals x. All right, there's y equals x. You can graph a function's inverse by reflecting it through y equals x. And you see that here with your exponentials and your logs. So if you ever get stuck graphing one of those two and you remember the other, use that reflection through y equals x to help you out. Right? So you should know the basic shape of a log function. You should know the x-intercept is at 1. You should know the domain and range. Yes, thank you. And you should know the vertical asymptote is x equals 0. All right. So there's your basic graph of your what we call your parent function, your basic log graph. Guess what comes next? If we graph the parent function, it's transformations. Hopefully that's purple enough that it'll show up on the video this time. You can actually tell that it's purple. What if we have that log base 2 of x graph and we add 3? Notice that plus 3 is tacked onto the end. Just like any other transformation, that plus 3 is going to move our graph up 3 units. So from our original graph of log base 2 of x, which we knew had an x-intercept of 1, and looked sort of like this, that whole graph is going to move up 3 units. Right? So that point that was at 1, 0 on our parent function is going to move up 3 units. So now it's going to be at 1, 3. Every value from that XY table on the last board will just have a Y value that's 3 greater, moving everything up. Shape stays the same. The asymptote doesn't move because we've got a vertical asymptote. Moving that up is not going to change that vertical asymptote. It's also not going to change our domain. It's also not going to change our range. Same shape, same asymptote, same domain and range, simply moved up on the graph. So now instead of this graph, we've got a graph that's further up. And we're just sketching here. So we don't have that 1, 0 anymore, it moved up to 1, 3. We don't hit the y-axis. We don't have a y-intercept because that's a vertical asymptote. We do still have an x-intercept. So let's talk about how we would find that x-intercept. Just like any other function, we'd find the x-intercept by making y equals 0. So let's actually solve this. Let's set y equal to 0 and see if we can figure out what the x value is that would make that happen. All right, trying to solve that for x. Subtract 3 from both sides. All right, and now go back and think about how we evaluated log functions. Well, we've got log base 2 of some number equals -3. Remember, that's like saying the x value is 2 to the negative 3 power, the base raised to this power. 2 to the negative third power, which is 1 over 2 to the third power, which is 1 over 8. So the x-intercept here, the place where y equals 0, x equals 1/8 for that x-intercept. Right? It's important that we can find those intercepts. When we use these in calculus next year, being able to figure out where the expression equals 0 and where the y-intercepts show up is an important skill for us to be able to solve, find solutions or zeros or roots of any kind of equation, not just polynomials. So there's using your transformations. Notice very little changed in that graph, simply moved up a little bit, and the x-intercept obviously moved along with it. So there's one transformation. We'll do one more, and I think you'll have seen enough to try these in class tomorrow. Let's do the log base 2 of the quantity x plus 5. Putting that plus 5 inside of that log function now moves to the left. So this graph, and I'll go back and we'll sketch in our original log base 2 of x parent function here first with a with an x-intercept of 1. We're going to move everything to the left 5 units. Now moving this to the left 5 units is going to move the asymptote as well. That vertical asymptote is going to move, instead of being x equals 0, it's going to be out here at x equals negative 5. That x-intercept, which used to be at 1, moves back 5 units, 3, 4, 5, to negative 4. So our x-intercept here will be at negative 4, 0. I didn't even have to solve that one. I could solve it. I'll do it real quick. If I made y 0 and thought, okay, what value would make this happen? Well, that plus 5 is now inside of my log function. I can't just subtract it away yet. It's almost like that log is acting like parentheses or like a square root would, like a grouping symbol. I've got to think first about the fact that this would be 2 to the 0 power equals x plus 5. So x plus 5 would equal 1, and now if you subtract 5 from both sides, you get x equals negative 4. So we could do that algebraically, but in this case, just knowing your transformation, we got that x-intercept right away. Shape of the graph stays the same. Did not move up or down. So basic shape, still the same. Vertical asymptotes at x equals negative 5. That affects my domain. Now I have x values that can be negative. Anywhere on the open interval from negative 5 to infinity. And you say, well, wait a minute, we just talked about how you can't take the log of a negative number. Well, notice, before we take a log in this function, we're adding 5 to that number. So if I had, say, negative 2 for x, I'm not taking the log base 2 of negative 2, I'm adding 5. I'm taking the log base 2 of 3, which is, I still don't know. But it's definitely a positive number, and it's definitely a value that we see on our graph. Our range has not changed here. Easiest question on our quiz will be, what's the range of this log function? The range of every log function is all real numbers. Go back to exponential functions. The domain of every exponential function, whether it was growth or decay, the domain was all real numbers. So if we switch the x's and the y's in an inverse function, the domain back from my exponential function becomes the range in my log function, right? And again, you can kind of think about doing a reflection through y equals x and getting an exponential curve out of these. All right, so that's how we graph our logarithmic functions and how we find the x-intercepts and the asymptotes and the domain and range.